All right, let's start. So last time we went through the classical probabilistic model. We went through the basic derivation of the model. So let's recap how we ended up where we ended up. So we said that the classical model is based on the probability ranking principle, right? And that probability ranking principle says that if you rank documents by the probability of relevance, decreasing probability of relevance, then you're going to have the best possible ranking. And we proved that that's the case for precision at any rank, recall at any rank, mean average precision, any metric that you come up with. Right? So the goal is really to estimate this probability that the document D is relevant given whatever representation of D you have. And that could include the query and all sorts of other things, right? So that's the best possible ranking. And then we made a number of assumptions about the random variables R and D and Q and the words that led us to express this probability as a rank equivalent to the following ratio, right? So the ratio over, you have a product of the words and the overlap between the document and the query, and it's basically defined in terms of the counts of the word W in the whole collection, in terms of document frequencies, right? And we got there in a formal way by taking this probability and making some assumptions and using the normal rules of probability theory to get there, right? So these are the assumptions that we made. So words are present or absent in the document. So we assumed that there is no frequency, and that allows us to have a single parameter, PW, for every word. Right? We assumed that all the words are completely independent of each other once you condition on relevance. So what that means is that we take this document, which is a set of words, and we can decompose the probability of a set into a product of probabilities for individual words. So that's where the product comes around. Then we made two assumptions, A3 and A4, which looked kind of strange on the surface, but they allowed us to restrict this product to the intersection of the document and the query. So there were two assumptions there. This is the empty document is equally likely under the relevant and non-relevant class, and if you have a word that doesn't occur in the query, that word must be equally likely under relevant and non-relevant class. And once you make those assumptions, things cancel out, and you are left with a product over the intersection of the document and the query, and that is nice because you can use fast evaluation methods for computing that product. And then we sort of were left off at this stage where we had to estimate the PW and the QW, right? PW is probability that the word W occurs in a randomly picked relevant document. QW, probability that it occurs in a randomly picked non-relevant document. Of course, we don't have examples of relevant and non-relevant documents. If we did, we don't need these assumptions. We just compute the maximum likelihood estimates. But if we don't have examples of relevant and non-relevant, we have to make some assumptions. And the assumptions that we made are that a collection as a whole set of documents is a pretty good representative of the non-relevant class. It's a reasonable assumption. So that's what allowed us to represent QW in terms of the document frequencies in the whole collection. And then assumption A5 is really an assumption that comes out of desperation. You don't have any examples of relevant documents. You really need to estimate PWs in some way, but you have nothing to estimate them from, and you cannot assume that a collection is a good representative of the relevant class. That would be silly. So you make a silly assumption that query words are going to occur in half of relevant documents, and that allows you to cancel out the PW and 1 minus PW, right? So, and these two assumptions together, they basically allow you to estimate PW and QW, right? Great. So that's how we got to the final form of the model. And of course, the whole reason we started this is we started with the TF-IDF formula, and we said, how can we make that better? And the answer there in the vector space model is, well, you tinker with it. You try and change something. And that is an infinitely long process. You're going to be stumbling around in a dark maze until you hit, by chance, upon a formula that works better. Right? Now we have something different. We have the final formula. We also have a path in terms of the independence assumptions that we made. So if the goal is now to take this and try to make it better, we have a recipe for doing that, right? When you have a probabilistic model, you want to make it better, what you do is you pick one of the assumptions that you made, a particularly bad assumption, and you try to relax it. You try to replace it with something a little bit more reasonable. So that's what we're going to try to do in this lecture in a couple of different ways. So I'm looking, these assumptions, they're all horrible to various degrees, but the one that seems to strike people the most is the assumption of independence between the words, right? That's the one that people usually jump at. They say, well, that is just plain wrong. You're saying that the probability of Barack, so the occurrence or non-occurrence of Barack doesn't tell you anything about occurrence of and non-occurrence of Obama. That's just false, right? So it's an assumption that's clearly false. So let's see what's been done on this front. Can we take A2 and relax it?